49 out of 55, which is something like probably like an 88% or somewhere around there. So the average is really high, you know, pretty good, right? Lots of A's, or a couple A's, lots of B's, lots of C's, not too many of them really bad. So we'll get those back as quick as possible. It'll probably be more like Thursday, unfortunately, because we've got a couple guys tested tomorrow. So do that. All right. Okay, now we're moving on to new chapter. And this is called Chapter 5. I'm going to freeze this. There we go, Chapter 5. Gases. Okay, just as a little, like a preview, gases are different than the other things we've dealt with so far. We've dealt with condensed states, we've dealt with solids and liquids. And if things are solids and liquids and they're pure substances, then weighing is counted. Okay? That sound familiar? Yeah. If we're dealing with pure substances, solids and liquids, weighing is counting. When we deal with mixtures, we counted by using molarity. Right? How many moles were in a given volume. With gases, it's a little more complicated. Okay, and the reason that gases are a little more complicated is because one, they're really spread out. You know, they tend to spread out. They don't tend to stay confined in an area. You know, if I have a cup of water, it's not like a cup of water all of a sudden migrates up into the air very quickly. There's evaporation, but I mean the liquid stays, just stays where it is. Same thing like if I have a lump of metal, you sit there, it's the lump of metal. But gases tend to diffuse all over the place. And so one of the things that really affects gases is pressure. Okay? The amount of pressure on the gas. You know, there's in your car tires, you know, there's a lot of pressure in there. And you would know because if you just push on the stem, that the air all just wants to get out of there, right? Because it's being crammed in there at a higher pressure than the outside atmosphere. Another thing that can affect gases is their temperature. Right? Did you guys have a lot of tire pressure sensor monitors going off in the fall? Right? Because the gas was affected by that temperature. Okay? In fact, you guys ever see dragsters do a burnout before they run? Okay, one of the reasons is to get the tire temperature up so it's stickier tire. But what's the other reason, John? You should know this.
Traction.
Okay, so for the traction on the tire, but there's another reason.
It makes it more inflated.
The air pressure builds up. Yep.
Yeah.
Yep. And so if you've ever seen like guys that run race like I don't know, like NASCAR and stuff, when they get a white flag, they're doing a lot of this, going back and forth. They're not doing it because they're bored. They're doing it to keep scrubbing their tires and keep the temperature up, so their operating temperature. So good. All right. So gases. Let's say we can say a few things about them. We can say they fill containers evenly. I got some really cool demos to show you eventually. I was going to do them today, but I really didn't have time to set them up. So, and the amount of notes I got to give you today is a little bit. But we'll bust out a vacuum pump here in a few days, and we'll play with it. We'll do some cool things. You'll like it. It's usually pretty fun. All right, so they fill containers evenly. So, you know, if you pour a liquid into a cup, the liquid goes to the bottom, right? Or if I put a solid into a cup, that solid remains its intact shape. It doesn't really conform to the shape of the container. But if I put gas into a container, it's going to fill that container evenly, right? So if I put air into my car tires, it fills the car tire evenly. It's not like some of the air ends up on one side and less on the other side. Okay. 2, gases are compressible. Gases are compressible. For the most part, liquids and solids are not. I can tell you one way you know that liquids aren't compressible. Do you ever do a belly smacker? It sucks, doesn't it? Because when your body hits it, the water does not compress. It's like you might as well be hitting cement, right? Until you break that surface tension, or you know how to dive very well. But if you hit it flat, you're gonna hurt. They mix thoroughly with other gases. They mix thoroughly. Oops. With other gases. You know, if I come over and I dump a bunch of trash on your lawn, okay, I dumped trash on your lawn, and it's on your lawn. Okay? But if I go ahead and I pump noxious chemicals up into the air, it's not necessarily going to go on your lawn, it's going to spread throughout atmosphere, right? Because gases tend to do that. I think you knew that when, well, many of you guys are already sophomores, but you don't have the sophomoric mind. That's why you're in this class. But the sophomoric mind, I don't know. I used to teach sophomores, and I'd find out this. Freshmen don't know anything. Sophomores think they know everything, and they fart a lot. I'm telling you. Did you notice that more in sophomore year? Guys kind of grow up a little bit between sophomore and junior year, for some reason or not. So that's why I always have air spray here, because when somebody farts, then that spreads thoroughly throughout the classroom, right? And then we spray that gas, and that spreads thoroughly out throughout the classroom, and hopefully we smell that, and not the other thing. But, all right. And they also exert pressure. Exert pressure. I don't think any of that is really surprising. So pressure. Pressure is something you'll talk a lot about when you get to physics. But basically it's a force exerted over a given area. A force exerted over a given area. So now, if you push on something, you're exerting pressure. That's like a lot of what wrestling's all about, isn't it? Exerting pressure over a given area. If you exert the pressure in the right area, you can get somebody to do something they don't want to do necessarily. Or we could say it mathematically, pressure equals force over area. Okay. So pressure, now what is it from? Okay, now from me, if I want to exert pressure, like I can physically touch something, put my weight into the push, and I'm exerting force, because I'm pushing, over a given area, however much my hands is, okay? The gases exert pressure. Now, how are they exerting pressure? Well, what are gas particles doing? What are they always doing?
Always moving.
They're always moving. They're always in motion. And so if you picture having like a container of gases, the particles are moving all over on the inside. All the different directions, crashing into each other, and I'll show you some things about that before it's going too. A neat little demo I got on the PC. But what pressure is a result of when those particles actually hit the container. Right? When they hit each other on the inside, they're not exerting pressure on the container. But when they hit the container itself, they exert pressure. So gases exert pressure. Gases exert pressure due to the force of the collisions. Due to the force of the collisions of the gas particles on the inside wall of a container. So let's consider a balloon. We'll look at balloons a lot, but this applies to a lot of other things. Here's my fancy balloon here. I have particles going every which way, but it's the particles that are hitting the container that are exerting the pressure. So think about it like this. When the container gets hit by a particle, that pushes on the inside wall, pushes out on the inside wall of the container, in this case the balloon. The thing is, though, is that there's not millions, there's not billions, there's not trillions, there's really huge numbers of these collisions taking place every second. So if it was just a few particles, you might see that container rippling, right? You get it, as one point gets hit, it would ripple out, but then it would want to recoil back to where it was because now there's nothing hitting it. The thing is there's so many collisions taking place at a given time. When you blow up a balloon, it looks like the balloon's static. But actually what's happening is just getting wrapped all over the inside of the container, but so often that it just looks like it's a smooth container. You get what I'm saying about the rippling kind of idea, John?
So what would happen when the balloon starts to deflate?
What's that? Well, okay, that's a very complicated question. One, usually the balloon starts to deflate because there's holes in the container of the balloon. It's not a perfect seal. So that's why most balloons deflate, okay? In fact, I would say that's the only reason that they really deflate.
So why do helium balloons last longer than like oxygen and air balloons?
Actually, it's the other way around, okay? Helium balloons actually deflate quicker because helium particles are smaller than regular air. Like air is made of O2, which is 32 grams per mole, N2 is 28 grams per mole, helium's 4 grams per mole. So it'll actually deflate quicker. Now, if you're talking of the difference between a helium balloon that's made out of that silverly mylar stuff, well, that's because there's no holes in those things. They're a much more sealed membrane. But if I took two identical balloons like these guys here, like one of these, and I filled one with air like that, and I filled one with the exact same volume with helium, the helium one's going to deflate faster because the little micro holes in here are going to leak it out quicker. And we'll play with a lot of balloons. Okay, so let's see. That's kind of redundant. Okay. All right, now atmospheric pressure. Okay, so our atmosphere exerts pressure. You're not as attuned to the pressure of the atmosphere because you've grown up and lived your whole life in it. Okay. Now I'll tell you, you can notice subtle changes to air pressure. Do you ever go down a big hill and your ears pop, or go up a big hill and your ears pop? Okay, that's the result of the pressure changing, and your eardrum is noticing that. And so on one side of your eardrum, there's air pressure pushing here. On the back side of your eardrum, you have something called the eustachian tube, which runs from the back side of your eardrum to your throat. And most of you guys know that when your ears need popped, all you go is go like this, right? And what you're doing is you open up that eustachian tube for a second, and that lets the two pressures on either side of your eardrum equalize back out. Right? So you can notice little pressures, but atmospheric pressure is pretty significant. Anyway, let's say. So this is the pressure that results. The pressure that results from the mass of the air in the atmosphere. From the mass of the air in the atmosphere. So, let's see. About standing here. Okay, we're above sea level, by the way. We're at about, I think we're around 500 feet above sea level here because we're sitting on top of a continent, right? Okay. But let's say we go down to the ocean. Okay, it doesn't matter where we are. The oceans are all at the same basic level. And if I were to look straight up above me, there would be several miles of air above me. Okay? Everybody buy that? Okay. And that air has mass. And it's pushing on us. It's not unlike going into a swimming pool and diving to the bottom of the swimming pool. Whenever you dive to the bottom of the swimming pool, do you feel the pressure build up? Absolutely, right? Well, water's a lot more dense, so you really notice that. But it's the same thing. You're basically in a big swimming pool of air, and you're at the bottom of it, especially if you're standing at sea level. And it turns out that, you might have heard these numbers before, every inch of your body, square inch of your body, has 14.5, it's like a 14.5 pound weight is sitting on it right now. And you don't notice it because you've always grown up with it, okay? You only notice when there's great deviations from that, like when you go down to the bottom of the pool. Now you're way over 14.7 pounds per square inch. Or if you were to go to really, really high altitudes, you know, that would be a problem, okay? So there's a lot of pressure on you even though you don't notice it.
Would being in like a building or anything change that, like the air pressure, because like it has the ceiling like blocked it?
Yeah, I know there's pressure issues in a lot of like really super high-rise buildings. Now, like a couple stories, no. I mean, we're talking you can get 50, 60, 70 stories, you can start getting those differences. That's partly why, like in those buildings, you never see any windows that could be opened.
Right.
so they can maintain the pressure. Because if you get a lot of pressure differences, that could cause some big problems with the structure itself. But yeah, that is an issue. In fact, like, do you ever see those inflatable dome things like Edinburgh has one? You know, there's no door that goes directly from outside into that thing, because if you did, and you opened up that door, all that air would go come flying out. So when you go to open those doors, they'd probably kick you in the face. You know what I mean? So usually when you go into those facilities, they have like a couple doors to go through. My understanding. So is that right? Has anybody been to one of those?
Yeah, it's usually revolving.
It would have to be a revolving something that keeps the pressure intact. Because if not, you know, they deflate the big thing, and that's kind of sucks. You know? Right. All right. So air pressure. Yeah. And so we can use air pressure actually to kind of predict the weather a little bit. You guys all seen that? When you have a high pressure, do you know what kind of weather you get in typical?
Aren't you getting a storm?
No. When you're under a high pressure system, it's usually cooler, okay, and it's usually clearer, right? Today, we're under a low pressure system. And in fact, I know that too because I was looking at my manometer over here. I'll show you that in a second. It's reading really high right now. But when you have low pressure, you tend to get more clouds and you tend to get more stormy weather. Now, you get most of the stormy weather when those things are changing, when you go from a high pressure to a low pressure. So again, when I think of high pressure, what I think of is, can you picture that like January day where you go outside and it's bitter cold but it's super sunny? You know, like that. Yesterday started out like that a little bit. You know. Now today, I think of this is more like a low pressure day when you get stormy weather. Okay. So you can help do that. Now, the way we measure air pressure is something called a barometer. And I have several barometers. We'll use them before too long. One I got is just this little dial thing. Over here I've got a barometer.